Hello everyone. So in the previous video, we discussed about the generation of the corresponding block diagram with the multiple DMNs and the different FFT IPs so that we can compare the effect of the burst length, effect of the clock frequency, and effect of the data width on the performance of the FFT accelerator. So our bit stream is completed. So the first thing we need to do is that we need to export the hardware. We will include the bit stream. Make sure that the folder is, the name is, and the addresses are correct. So once the exporting the hardware platform is done, then we need to launch the IIT's IDE. So again, here make sure the address of the folder is correct. So here, in case you get this screen, you need to click on File and New Application. If you get the startup screen, again there you need to click on the Create Application Project. So in the application project, you need to add the XSA file. It is there in the same folder where you have created your hardware files, block diagram. So you can see that there is a XSA file. So this file has all the details about your hardware block diagram which you have created. Click on next. Here you can give the name for the project. Okay, so here you can see that the initial project with the Hello World will be completed. Now what we are going to do is that we are going to first check whether the Hello World is working fine or not before we modify our project. Okay, so this is my Hello World code. Since I am using the same USB for the JTAG as well as for the UART, so I'm going to map my output of UART on my JTAG cable via debugger, so that I don't need to use the two separate USB for the zedboard. Okay, so this is the change I'll be doing. Then you can see that all the 5 DMAs are there. So our BSP is the latest one. Okay, so then let's focus on the debug. First, build the project. In the SDK previous version, though, usually the projects gets built automatically. Here you need to make sure that you manually build the project every time you test it on the hardware. So then debug configuration, system project debug. So I'm using the local board. I'm going to test the this one. So let's see. So you will see that the blue LED on the zedboard is glowing. That means FPGA has programmed, and now the processor is also running with it is stopped at the first line in the code. So now instead of using the separate cable for the UART, I'm going to use the JTAG terminals. So I should see all the display on this screen. So let's run the code. So you can see that the code is working fine. So that means my entire setup is correct. So now what we are going to do is that we are going to copy the code from the previous lab and use it here. Okay, so we have added the code with certain modification. Now you can see that I have the 5 functions for the 5 DMAs, and then I'm calling them 2 times. One when the cache is unable, data cache is unable, and second when the data cache is disabled. Okay, all the 5 functions are same, except that in the ACP port function you don't use the cache flush and the cache invalidate one. In case of the HP, you need to use the cache flush and the cache invalidate functions. That's the difference between the HP and ACP as we discussed last time. Okay, so with this now we can move to the testing. Now, since we are using the large size array, we need to increase the heap size so that we have the sufficient space to store this large array, because each array is of the size 1024 and then they are complex floats, so that's a huge memory requirement. So the first thing we will do is that we'll build the project. Okay, so there is no issue in the project build, and then let's go and test it. Okay, so first I'll run the first function, which is the short burst and the ACP port. So you can see that the execution time for PS is 1119 microseconds, and for the ACP port with the short burst, it's a 74.78 microseconds. Now let's see what happens when we use the ACP port with the 256 burst size. Now you can see that the PS will remain the same because we are just running the PS the same again and again. But you can see that the ACP port is the execution time is reduced significantly. So that means by choosing the burst length appropriately in the DMA, you can get the significant improvement in your execution time. Okay, now let's compare the HP port and the HP fast port. Okay, the one with the 100 megahertz clock frequency, another with the 240 megahertz clock frequency. Now you can see that the for 100 megahertz clock frequency, your time is 90 microsecond, which is higher than the ACP with the short burst. But when you increase the clock frequency, you can get the significant improvement in your execution time, which is 64 microsecond. So you can see that by using the higher clock frequency in the FPGA, you can increase the acceleration factor. Then we will now move to the smaller word length, and you can see that when the word length is smaller, that is 32-bit, obviously single for every data transfer you need to do the 2 transaction, and hence your execution time gets worse. So the word length is the data bus length is very important. You need to choose it appropriately. Okay, now we will discuss what happens when you disable the cache. Now the ACP port is getting the advantage because the data is present in the cache, and ACP port is getting access directly from the cache instead of the DDR. But now because the ACP, the data is, there is no cache, that means data needs to be read and write from the DDR. So now you will see that the ACP port performance gets degraded. In addition, the performance of the processor also get degraded because now processor instruction and data is present in the DDR. So the processor performance gets degraded. So let's run to the last function. So now you can see that the processor has performance has significantly degraded from around 1000 microsecond to 13,000 microsecond. That is the degradation in performance. And at the same time, you can see that the performance of the ACP has also degraded. The performance of the HP port has not degraded because for the HP port things remain the same. Okay, you can see that for the HP port there is not much degradation, but you can see that the degradation happens because your processor has become slow. In case of the HP port, processor has to configure the DMA, it has to run the this part of the C code, so the processor performance has degraded. So that is the problem why the HP port, you can see here it is taking 90 microseconds, and here it is taking 78 microseconds. So you can see that the HP performance has actually slightly improved compared to the when the cache is disabled, because you don't need to do this cache flush and the cache invalidate, because those functions need not to be executed. So that's why you get the speed up in time. Okay, so that's it from the today's video, that you can see that the by using the you can see that by using the appropriate clock frequency, word length, and the type of the port, you can get the significant improvement in performance. So the next thing we will check is the cross triggering, like how to trigger the FPGA from the processor or processor from the FPGA. Now to do that, we need to do some changes in the block diagram. For example, if you go back to the block diagram, we have not added any signals to be observed inside the FPGA. Okay, so what we will do is that we will modify the block diagram to add few signals. So we will add all the signals which are input to the processor as a debug, all the ACP, HP. Okay, so we'll add all these signals, and then we will look at the difference between the short burst and the long burst. I think that also we should be able to observe it from here, because that's what the burst size indicate. But so this is the is short burst HP. HP is the word length we will be able to observe. Okay, so let's observe the output of this both the DMA. Okay, so for the right now we'll add only these signals. We'll do the run connection automation, add all the signals, click on OK. So you can see that the ILA has been added. Now we need to generate the bit stream again and then repeat the process. Okay, so I'll close the YTS IDE. Okay, so I'll validate the design. Okay, validation is successful. Now I'll generate the bit stream. Okay, so our bit stream has been generated. So we'll do the same process as we did last time. We'll export the data again. and then we launch the IIT's IDE. So few things you need to take care is that now since the hardware files are updated, you need to take care that you update the BSP. So update hardware specification. Okay, so the hardware files are updated. Now let's build the project. Okay, so now let's test the code. Okay, so the code is working fine. So now let's enable the cross triggering. So for the cross triggering, we need to follow the same process. The first thing we need to do is that we need to, in the debug configuration, we need to enable the cross triggering. And here we need to enable the cross triggering from CPU to the FPGA, and another thing from the FPGA to the CPU. Okay, so click on apply and then let's do the debug configuration. So now once the FPGA is programmed, we should look at the hardware manager inside the Vivado to see the ILA signals. Okay, so what we will do is that we will have the trigger from FPGA to the so we'll have the trigger from the we will have the trigger set up here, and what we will do is that we'll see that whether trigger in the FPGA is working or not. Okay, so whenever something happens on when the some corresponding event happens, we need to make sure that the processor stop at that point. Okay, so this is trigger from FPGA to the processor. So let's look at the M2S port. So memory to stream, we'll see that let's look at the what we can set up AR. So memory map to stream. So we are doing the read operation here. So let's look at the R last signal and see that there is a transition on the R last. So 0 to 1. In the trigger setup, we need to make the trigger out. Okay, so we have to provide the trigger to the processor. So now you can see that it is waiting for the trigger, and let's run the code. So you can see that the trigger has happened in the FPGA. You can see the trigger has happened on the last signal and your processor has stopped at that point. So this is when the particular events happen inside the FPGA, the processor stops at that point. Okay, this is called the trigger from the FPGA to the processor. Now let's see that whether when you stop inside the processor, does the trigger happen here? Okay, so what we need to do here, we need to disable the trigger out. Okay, basic or trigger in. So now we need to see, okay, it should be only trigger in. So we need to see that whenever we stop the code inside the processor, the corresponding data should be captured inside the FPGA. So I'll stop the code here. You can see that the data has been captured inside the processor. So the corresponding trigger has happened. So let's see why the code is not working. Yeah, so code is working. So let me run it again. Now let's stop the code till this point. You can see that the trigger has happened. So when the corresponding event has happened inside the processor, the FPGA captured the signal at that point. So this is called as a cross triggering. Okay. So with this, we are done with the today's lab. So here we completed the comparison between the different combination of the ACP and the HP